Right, hello everyone. Today we are going to be talking about virtual Finality Gadget, which is a mechanism that enables general purpose rollups to achieve finality on the base layer. And this is non-technical talk actually. Will be so if someone is already like building their own like rollup and like, connecting their sequencers and DA layers like from Celestia and so on, like maybe you will rediscover something, some new perspective on like what rollups are, how do they, where we can find them, and what their use case is, and like what kind of cool new things we might be able to do with them. It might be a talk for you, and also if you have no idea what the rollup is, it's probably the good presentation for you. And so let's begin. We're starting with a formal definition of rollup because it's sort of hard to find a formal definition, and most of those concepts most of the time are like sort of made up, right? So it's better to like formalize something so that we know what we are talking about. And so most of the time people talk about like this, something happens off-chain, something happens on-chain. I try to avoid saying on-chain and off-chain. I think it's better to talk about on the base layer and off the base layer. So then because the rollup does not necessarily has to be something created in the context of the blockchain itself. Actually, with general purpose rollups, we'll be experimenting with a concept of the rollup that not necessarily is a blockchain application or has anything to do with a blockchain application. And yeah, so what is a rollup? Is basically some form of the base layer computation that impacts the state of the base layer. And currently, like there are quite few different types of rollups. Like people say, like there are like those optimistic rollups, pessimistic rollups, like ZK rollups, right? What they differ by most of the time is the way we decide how those changes that are occurring off the base layer are finalized on the base layer. So what I mean, for example, in optimistic rollups, whenever like that we commit some proposal for the base layer state change, we just assume, okay, it's correct. Like you don't have to verify or say anything. But if you spot that something is wrong, right, you can submit a fraud proof and be like, hey, something is wrong. Let's not have the state committed. In case of pessimistic rollups, we're talking more from the perspective of like, I don't know if this is correct, right? I think it's best if at least n people verify that it is correct, and like only then the state transitions can occur. And to sort of make our life easier, we will try to introduce something which we'll call just general rollup, right? The general purpose rollup, something that encompasses both this like pessimistic way of achieving finality or optimistic way. Like it will not matter in our examples. So maybe let's start with like why do we even need it, right? Like why do we need rollups? Like if you want to have a decentralized network, right? The decentralized network, which is because what's the point of decentralized network? Their point is to democratize access to finance, right? To money, to unbank the banked, right? And if your blockchain is clogged with state, which is pure malware, like which is like full of something that is not really useful for you, you still have to pay for it, right? Like if there is like some crappy application running on EVM where anyone can commit the code, right? Then if you are not interacting with this application, you still have to pay for it, right? And in the context of application-specific blockchains, like it's even more problematic because it takes a long time and a huge effort to actually have your blockchain-specific application. It costs millions of dollars, like to create this application, to have people come together and like have all those validators onboarded and like raise the money and like do your project. It's like you're time to deployment is very long. So with the rollups, like sort of like the expectation is like, hey, we don't even have to care about blockchains. We can deploy applications much faster, much cheaper, right? Like if we can go down to the cost of deployment close to Ethereum, right? But we have much more access to much more useful resources. That's where the rollups will come into play. And because those EVM chains or whatever other applications, they are pretty limited when it comes to resources. Like, what can you do on EVM? Like, I don't know, a couple of multiplications, right? Division, write something to some register. Like, it's not really that exciting. With rollups, what we can do, we can plug in any resource we want and have some interesting application. As long as this application is deterministic, we can have something much more powerful running there. So we're going to have an example of a general rollup, and this is going to be our Lambo swap example. There is going to be an execution part of the general rollup, and there's going to be a verification part of how does this general rollup comes into finalization. Right? So in our case, the Lambo swap application is some sort of deterministic application. What it means for the application to be deterministic, it means basically that whenever the same sequence of inputs come into the black box that we have in the middle, we expect the same thing to come out on the other side. And that application could be already running, like in our case, for quite some time. And we have some state as t-1, something that happened in the past, and we have 2 Lambos in our Lambo swap, right? And maybe there is some new input coming from the base layer chain. And for example, oh, someone is depositing like 2 Rollexes to our Lambo swap. And then once our Lambo swap gets aware of this, like knows what the old state is and gets aware of this new inputs coming in, the user that like made this input, maybe he can make some operation, right? In our case, we have like a swap operation. We'll try to swap 2 Rolexes for a Lambo, right? And as the result of this computation, we might get different output of this depending what kind of rollup that is, right? We might get some proof of execution if we are using ZK proofs, right? If we are using optimistic rollups, maybe just like some batch of transactions where the root hash gets committed on the base layer, and we just have like some new up state and maybe some possible output that a user can then take off this rollup, which is most often, at least in the EVM, represented like just some smart contract where you lock the assets, right? So if you show the proof that Merkle proof that something Merkle proof that your withdraw transaction is included in this root hash, maybe you can take out your Lambo. So in our case, we don't know, right? Like we had this state transition, and we don't know if this is correct execution or it's not correct execution. This is the question we have to answer to ourselves, right? Was this state correct or not? And like we need some, in this finalization process, some informations, right? What informations do we need? We need to know what happened. So we need all the inputs that came in. We need are there the ordered inputs? In certain cases, we don't even need the inputs. We can just have a proof of execution being correct. This is our ZK proof example. Of course, we need the previous state that the application was in. We need the new state of the application. And this base layer input, we also need to be aware of all this information to be able to verify it, right? And this verification logic is what allows us to answer, was the state transition of getting this 1 Lambo out correct or not, right? Like you cannot take 3 Lambos. This doesn't make logical sense. And what interesting in case of general rollups, which differentiates them from optimistic, pessimistic rollups, is that this execution part has to be deterministic. The verification part doesn't have to be deterministic. And why, we're going to find out a little bit later. And yeah, so let's get back into it. So if we look from like a higher level perspective, all those things are actually the part of the same puzzle. It's all fully recursive. And that's why I started with formal definition, because if we define the formal definition as I showed in the first slide, then we find that this definition allows for full recursivity. We find out that, oh, maybe the optimistic rollups are a type of a pessimistic rollup in which the number of verifiers is 0, right? Because we optimistically assuming that it's correct, so we don't need the verifier, so optimistic rollup is a type of a pessimistic rollup. But at the same time, we can say like a pessimistic rollup, maybe it's a subset of something bigger, maybe it's a subset of some general rollup in which we don't know, like there can be a number of verifiers, and the code for verification doesn't have to be deterministic. In case of pessimistic and optimistic rollup, we have a very predictable way in which we verify that the application arrived to the state that makes sense. So when we talk about this, why did I use this word general purpose rollup? Because I want to introduce the concept of like general compute. But general compute in the context of rollup, from the context of like blockchain-less, completely blockchain-less application, has a couple of problems. Couple of problems that like normal types of rollups don't really address. And those are like, they could, but they are not really designed for that. Like you have things like, oh, hey, like we don't really need blockchains. Like we might want to have multiple parties cooperate together and pull up resources. Maybe we would need to have our verification logic to be slightly more fancy, because there's a lot of problems with like a blockchain applications, right? Like no application is perfect. Right? It's expected the application might arrive to the state that we didn't expect, and this because we are humans who actually run all those applications. It's actually our decision. How do we want to interpret what happens on chain? It's better to have a transparent process for this than to have this hidden process where, like in Ethereum DAO, oh, if I lose the money, right? It's like, oh, just forking out. But if you lose the money, oh, fuck you, right? So in this case, like, what does it tell us? That the verification logic is not logical. This code not always arrives to logical state. And if we want to have some cool applications, right? Not type of applications where we say, oh, we don't have enough resources, right, on our EVM trying to play this game. What if we duplicate EVM chains to like 100 EVM chains? Will that solve a problem? We have 100 rollups for like some session part of the game. Like, it's not really useful, right? There has to be completely different solution that enables us to have this type Web 2 type of applications, which are not perfect, and games are the best example of that. If you play something like Minecraft, right? Maybe you are familiar with Moonbeam on Polkadot, right? You know, like the game admins still need to have like a video stream from you playing the game, and in real life see, okay, were you cheating or were you not cheating this game? Because we are interested mostly in humans. We are not really interested in this application itself. We know it's imperfect, and that's why we have humans, and we need a way to allow not only verify a code in like one specific predefined way, but also enable anyone to decide what is their own logic for unit testing, verificating what is really going on. So here comes the virtual Finality Gadget to the rescue. I'm going to show at the end how we in particular implemented it. But anyone can do it. It is like this idea anyone can try, experiment with for themselves. And what we are trying to achieve with the Finality Gadget, we want to try to give the developer ability to define the way that he wants to verify his application, right? Maybe today we're using ZK proofs. Maybe there's some like a good way to do ZK proofs, but tomorrow there's going to be a new way to do ZK proofs, right? And like we need to not only be able to update what the application does, but we also need to update how do we verify that this application is running correctly. Maybe there'll be better ways to verify something. So we want to give this power to the developer to, as he submits to the chain, like, hey, I want this application to run in this specific way. Maybe someone picks that work out. We also want to give him ability to like, hey, you can also, this is the way I suggest you to verify it, but there are many infinite ways to do so. And this is what we're trying to achieve. And when we think about all of this from this perspective, hey, there can be like many verifiers, many ways to verify something. Like we come to the conclusion, yeah, all this thing is fully recursive, right? The blockchains themselves are a fancy case of a general rollup in which you have multiple people collaborating together to create a block, but our fancy verification logic here is basically all people coming together being like, oh, like we're running the same thing, right? So in the simplest case scenario of a blockchain, we just have multiple executors and multiple verifiers that literally rerun the same thing, which it's all fully recursive, it's all part of itself. That's why we need this definition of the rollup to be as defined at the beginning. So we in particular, as we designed our application, like our VFG, we are particularly working with rolldowns. It's something that you might just have recently heard also from the Polkadot, that they're introducing this concept of a roll down instead of a roll up. And basically what's the difference between a roll up and a roll down is that roll down is intended very particularly for a monolithic stack of things. You can think about it from like, oh, Microsoft Corporation has its own like Excel, OneDrive, like all the tools and things that you need to use your operating system. It's all packaged together, right? Like you cannot expect that like on your Apple device you're going to have a great experience with OneDrive and like going to work perfectly with everything. Like it's very hard to have this kind of live in this kind of world like where Celestia is like, hey, like everyone can build this app, it works with everything. Like, does this work really in real life scenarios? It's like, maybe if you have like $1 billion raise, like maybe it's possible. Like, but if you are like a smaller project or just like exploring this concept for yourself to experiment with something out of the box, like maybe this is a solution for you. So in our case, like we work specifically with a roll down. It's a type of a roll up which only exists in the context of a monolithic chain. So it's like Polkadot, for example. And I think before we go to our example of how we implemented it, I think it's like we should give a shout out to a couple of people, like without which we would never be here, right? Like Jay Kwon, right? And who is the founder of Tendermint and Cosmos. Like without him, like none of us would be here, Celestia wouldn't be here, all the modular Nebular Summits wouldn't be here. But also we cannot forget about true creator of the pessimistic roll downs, a person like started this entire rollup movement, and that's Joseph Poon, the creator of Bitcoin Lightning. Bitcoin Lightning is the very first example of a pessimistic rollup. As per definition that we showed before, Bitcoin Lightning payments channels is a type of a pessimistic rolldown where execution happens off-chain, like people exchange between themselves transactions, and at the end of the day, they finalize them by saying, okay, this is the final state, we like run it off-chain for quite some time, and maybe there was a million transactions happening, and now we're just using a single transaction to say, this was correct, and on top of that, everyone comes to the consensus on, yeah, that execution was correct because we committing hashing power and confirming this block over time, and that finalizes this pessimistic rollout, which is Bitcoin Lightning. So this was an example of a pessimistic rolldown, and here is our example how we are implementing it in for Kira in particular. We have our stack is separated into 3 components. We have a backend part, which we call our blockchain, like our base layer. We have a middleware part, which we call our Interx. It's a shortcut for Interchain Nginx, is a decentralized API, which can create fraud proofs that enable anyone to verify, oh, like my RPC request coming from the node that it's supposed to, and if it's incorrect, I can check it against another node and like have a fraud proof that it wasn't correct. I can evict the guy because we're using governance permissioning to become a validator in our network. You have to be permissioned by the governance of this network, and this way you cannot, once you have malicious actor, you can evict them. So in our case, people have money at stake. They also run the middleware at the same time. So if they do something sketchy, then can be kicked out by the community. And on the top of that, we have the user interface, which is also decentralized because it's static. It can be hosted in IPFS. You can just download the HTML file, interact with it on your machine. So as from the front-end application running in memory of your browser, you can access the backend through the middleware. Every single part is decentralized. This is how we intended it, because light clients were very difficult to maintain, as we see with Polkadot. And on top of that, we have our execution part, which is our VFG part. So from the context of our platform, like we don't really care what the type of application is, right? What we care is that the application is deterministic. As long as the developer can create a deterministic application, something like, for example, REST API server in Python, whatever language you want, we don't really care, then you can propose that, hey, like, guys, I want this application to run. There are specific resources that I need for my application to run. Maybe there's like some ML or there's some other like AI app. Like we don't know what the application is, but hey, like I'm specifying in my config, like this is the Docker container, the Docker image that I want to run. This is the resources I need. Hey, is there anyone who wants to run this application? And people, our validators can come and be like, hey, I want to run this application. There are some incentives for you, right? If you, because this is also an account abstraction in our case, so like our applications are able to interact with the base layer just as if they were normal users. They can issue tokens, they can do any operations on the base chain, they can communicate between each other using XAM, cross-application messaging protocol, which we also developed. And so that's the execution. You have to be a validator to be an executor. All you do is literally pull the container and run it. And you can also join the network as a verifier. So anyone can be a verifier. If you have an interest in this application, if you have some tokens of this application, you can be permissionlessly verifying what this application does. And if you don't have money, you can just be whitelisted by the people, by the owner of the application, which, by the way, since it's account abstraction, can be also an application itself. It's like one way which you can develop your VFG, but there's like literally infinite ways through which this can be done. Like I see like people are already by the window and waiting for their turn. So thank you. And in a second, like just you can find us at kira.network. And I don't think they are chasing us away. So if anyone has any questions, it's go ahead. In this case, that I mean, like yeah. So in our case, the way we develop, because you can develop anyway, you are forced to be a validator to run an application. There has to be at least one executor, right? In order for like application to exist, but this single validator can run many applications. Like nothing stops you, but of course you need to have resources, because every application will commit on chain a message like, hey, this is my binaries, this is like, but those are resources I need, right? And different validators will have different resources. Like some will run, I don't know, Raspberry Pi in Africa, right? Here we go back with this flashback of our chain, where our chain has to be super lightweight, so people can access it anywhere. Like if you have a gigabyte block, like sorry, like, but your network is not decentralized, right? It's literally impossible. It's pure bullshit. It has to run in Amazon. There are different slashing conditions most of proof-of-stake networks always have that force you to go to a data center, right? We want to live in a world which, like, hey, we want to have access to those resources that maybe exist in the data center, but we also want anyone to be able to access it.
So do you also run something like proof of resources, just like Filecoin and networks?
You don't have to, because you will get evicted by the application owner.
Oh, okay, so if it
right.
doesn't work properly,
The token holders literally will make a proposal, because you can abstract the way. By default, when you start your application, it's sort of like an Ethereum, right? You have an owner of a contract, and the owner fully controls it until he gives up, right, his ownership, right, to maybe token holders, however he coded it. And yeah, so that's what you can do.
So I think it's pretty cool, and I guess it works out for static, and like you mentioned, constrained, I guess, applications. What about for dynamic applications?
So the cool thing is, like, we developed our front end just for our network. This front end is not intended for your application, right? This application has to have its own front end. It can be static, it can be game. We don't know where the heavy work actually happens on your computer, because you need the graphics, to render something. The game server, like, I don't know, like RPG game will just tells you, okay, where are the players, what you should see, right? What we did, however, for you is we have this middleware part, right? This interacts, which proxies the request. You can use it as an API of your own, which is proxied. It orders your transactions. The only limitations we have is basically you have to use HTTP for input, because this is the easiest way for us to order those transactions. However, for output back to the user, you can use TCP or UDP protocols. Is not the problem. In your configuration, when you say, hey, I want this Docker container to run, you also have to say, like, hey, I need this port to be proxied, and I need this kind of, this for UDP, this for TCP. So like when you have your video game, maybe you have to, okay, maybe there is streaming when it comes to like updating where the players are, but when you comes to you interacting with it, it's just like, you know, RPG, maybe you just like do one click a minute, right? So the speed is not that important, right? But at least you have like, you know, you don't need the blockchain for it. So yeah, and since it's recursive, as we talked before, right, it's like, you know, I think it's the formal definition is much more correct than like whatever other people are proposing.
Nice, thanks.
Any other questions? All right, so thank you guys.